Luminescence geochronology, and so that we're getting closer and closer to present as we go down the different dating techniques. Luminescence dating is roughly divided into two different techniques. There's OSL dating, or optically stimulated luminescence, which is the production of light through the stimulation by light. And then the other one that you've probably heard of is thermal luminescence dating. And we're dating about the same thing, but we're using heat to cause minerals to luminesce. Overall, both of these techniques are dating the last time that quartz or feldspar minerals were exposed to either heat or light. So in the lab, the only difference is what we're using to stimulate them. And today, most people use OSL dating over TL dating. And the reason is it's like going in with fine dental tools to measure that luminescent signal versus hitting something with a sledgehammer. The heat is very effective at causing luminescence, but it can cause luminescence I'll discuss the mechanism, but you can actually be sampling traps that are much deeper than were zeroed at that zeroing event. So this is just kind of a background on luminescence dating technique. The technique actually was developed in the 60s based on first looking at some marine sediment. And then at that time, we were only using TL dating. The idea of OSL dating wasn't developed until 1985, when Huntley et al. Published a paper in Science saying, hey, I think we can use light to measure luminescence. And the instrumentation had been developed to the point where you imagine the difficulty. We're using light to measure light. So we had to have very sensitive photomultiplier tubes to measure the luminescence given off by these grains of sand, and the filters so that we can stimulate in one wavelength and measure the light given off by the other wavelength. In the year 2000, there was the development of the modern techniques that most everyone is using today. And I'm not going to go into them that much, but there's different ways that you can measure luminescence. And also the development of single grain dating. So we've gone from moving from small aliquots, for big aliquots of sand, to small aliquot, and now to getting an age on each sand grain. Like a lot of these other techniques, we can do that with luminescence today too. Here's some pictures of some quartz sand. These are aliquots of sand that are 1 centimeter in diameter. And so these are very large sand grains that we're going to date things that are only 250 microns and smaller in diameter. But for this specific picture, they put on some big whopping sand grains, stimulated them with light. So this is what they look like under normal lighting condition. And then using filters, they're showing what they look like when they're luminescing. And the different colors here is because the different filter that was used to detect the light. So this one's looking at a red luminescence given off, and this is looking at a blue luminescence. One of the the take-home messages, these are really good samples. These samples were chosen to display the luminescence, but you can see that there are certain sand grains that are much more luminescent than others. And if we were to go outside, everyone grab a handful of sand, probably only 1 or 2, maybe 10 sand grains out of every 100 actually would luminesce. So not every sand grain is born equally with its ability to luminesce. And so I'll talk a little bit about that later when we talk about single grain dating and why we need to analyze thousands of sand grains to get 100 that we can actually use for dating. But yeah, there's a lot of variability, and it's dependent on the geology of the source area and the life history of that sand grain, how many times it's been moved around and beat up on the landscape. These are quartz, feldspar. We also date feldspar. Feldspar are typically much brighter. They luminesce more readily, but there's a number of problems with feldspars too that kind of limit their use. So the general idea, the luminescence technique provides an age estimate for the last time that sand, being quartz and feldspar, were exposed to either light or heat. And that's what zeroes the luminescence signal. And I'll talk a little bit more This is exactly how that works, but the general principle is the last time it was exposed to light or heat. After burial or removal from that light and heat source, the luminescent signal grows with time. And that's due to exposure to radiation in the surrounding sediments. So every handful of sand has a little bit of uranium, thorium, potassium, rubidium, and the decay of those radioisotopes produces this radiation that actually generates the luminescence. In addition, we're also interested in cosmic dose to the sample. So if it's in the upper meter or 2 or 3 meters of the Earth's surface, it's getting a significant part of the dose, and the luminescent signal is coming from cosmic radiation. And then we bring it in the lab. I'll talk about how we actually get it to the lab without exposing the sample to light. And we measure the luminescent signal. And we also make another measurement of the radioactive environment, and that's how we get the age. So we need to know both parts. How much luminescence and how radioactive were the surrounding sediments. There we go. This is just a simple line diagram explaining what I just talked about. So you'll have sand grains. Every sand grain has a previous history, will have been exposed to radiation somewhere, and will have a luminescent signal if it does luminesce. And then it's brought to the Earth's surface, and it's moved around on the Earth's surface. In a river, in a sand dune, on a hill slope, by a glacier, anything that brings the sand to the Earth's surface. And usually these sand grains move around on the Earth's surface for some time. And if they're exposed to sunlight, in this case, I'm not talking about thermal resetting here, but when it's being transported, it's exposed to sunlight and it's bleached, and we call that bleaching. And that brings the latent luminescent signal down to 0 or perhaps near 0 if it's not in a very effective bleaching environment. Sample is deposited, and then that little sand grain is exposed to radiation and it acquires a luminescent signal over time. For most of the time period, it's going to be linear, but once we start reaching the point where the sample starts to saturate, you do start to see it changing from linear to starting to saturate. You don't get a nice one-to-one relationship anymore. Here's our sample in the ground, surrounded by feldspars, mica minerals, incoming cosmic radiation, alpha, beta, gamma, and cosmic radiation all can generate luminescence in the sample. So we're worried about all of these different sources of radiation, and that's what's characterizing our dose rate environment over time. So how does little sand grain develop a luminescent signal? Where exactly is that coming from? So we have this radioisotope decay, and we're looking at a specific type of radiation that's high enough energy that it can ionize. Otherwise, it can eject an electron from the mineral from an atom. And so exposure to that radiation ejects electrons within your actual mineral that you're looking at. Once that electron's been kicked out, it can do a number of things. It can just go right back to the atom that it was orbiting, or on occasion, it enters kind of the interstices of a crystal lattice structure, and because it has a negative charge, it could get drawn to a location that has a positive charge. And those we consider defects in the crystal lattice structure. Those could be a point defect. Could be a, instead of, so if we're talking about quartz, it should be SiO2. Maybe there's a sodium or a potassium or a titanium or something else inserted into that crystal lattice structure. Or maybe we're missing an oxygen, so there's an oxygen vacancy. Anything that has a slight positive charge, that electron can be drawn to. And it will sit there in that space, the ones that we're interested in at least, will sit there over geologic time until stimulated by energy to be released from that trap. And we call these luminescence traps. It's very specific. It's like 2 electron volts charge that needs to hold that electron in place. We don't want one that's held so tightly that it won't be released through exposure to something like just sunlight. So we want a very specific group of those electrons. But once your sand grain is exposed to that external stimulation, the energy that it absorbs it kind of excites that electron out of its current state, and it can be released from that trap and fall back down into a lower energy state, at which point, because it's dropped from high to low energy, it can release a photon of light. And that release of light, due to that change in energy state, is the luminescence that we are measuring in the lab. And of course, there's a lot more to this, but it's pretty much just kicking around electrons within a crystal lattice structure. This is an energy diagram, kind of trying to display what I just talked about. So you have electron, it's sitting somewhere. It gets hit by ionizing radiation. It's kicked up through the conduction band, and then it falls into one of these positive defects or traps in the crystal lattice structure. At which point it is hit by, it could be light. Typically I'm talking about optical resetting, but it could also be heat. And actually heating the sample will give the electron a little bit of energy. And if that energy is enough, it will be evicted from that trap, and it can fall down into a lower energy state. So this is energy here. And upon recombination at that lower energy state, we'll have excess energy, which is released as that photon of light. It doesn't have to do that. It could fall into a similar energy level trap again. It could go right back into the same state. There's a lot of other things that can happen that you won't produce luminescence. But enough of them will fall into one of these lower energy states, which is typically an atom that's missing an electron in its orbit. And if that happens, a photon of light is emitted. Okay, so to calculate an age for a sample, and I've pretty much said that, but I'm going to just restate this. The age calculation is dependent upon our dose rate environment, so how radioactive the sediments are that little sand grain was exposed to. If you have lots of uranium and thorium and potassium-40, really shallow sample, lots of cosmic radiation coming in, you're going to have a lot of electrons that are being ionized and can be ejected and fall into these traps. So that's one part of our age equation, is understanding the dose rate environment. We spend a lot of our time working on the other half of the equation. This is usually made, this measurement or this determination is usually made with a couple measurements of the sediment. You don't spend your whole time working on this, but it is half the age equation, so it's very important. And collecting the proper sample and getting good measurements of the dose rate are equally as important as understanding the luminescence, which is the second half of the age equation, which is measuring that OSL signal. And then that's all we know. You put it into the machine, it luminesces. But we need to know how much radiation caused that level of luminescence. And so this is where all of our time is spent, is going through a set of experiments where we're dosing the sample and measuring its luminescence response. Dose, measure, to try to understand and bracket the actual radiation the sample is exposed to produce that luminescence signal. So that equivalent dose of radiation that was required to produce the natural luminescence signal is called the equivalent dose. And those are our two ends of our age equation. So the definition of the equivalent dose, I just described it. I guess I didn't need to put this here, but it's the equivalent dose of radiation required to produce the same luminescence that the sample produced when you brought it to the lab the first time. It's measured in units of grays, which is an energy measurement. And we assume, so here there's always assumptions. Every dating technique has assumptions. We assume that what we measure and what we determine as our equivalent dose is the same as the paleo dose the sample actually received during burial. But we'll never know that paleodose. We only know the equivalent dose to back out that luminescence signal. The dose rate, it's a rate term, so it's the amount of radiation per unit time. We have only one dose rate that we can use to divide the equivalent dose by. So we make the assumption that that dose rate has not changed over time, or that at least we can calculate a good time averaged dose rate, looking at the radioactive environment of the sample. If you've had things changing, if you've had weathering or dissolution of minerals over time, you've maybe moved your sample depth, so you've moved in and out of cosmogenic radiation and how much is the sample's receiving. Those are all things that are included in uncertainties. Again, the units are grays per 1,000 years, or if you're working with really young stuff, sometimes people do milligrays per year. But I'm usually a little bit on the older side. And this is based on the radioisotopes in the surrounding sediments. And the ones that we're interested in are uranium, thorium. We've heard a lot about that. Potassium-40, we've heard a lot about potassium. Rubidium is a minor contribution, and then the cosmic radiation the sample receives. We get these measurements either directly in the field by inserting a gamma spectrometer into the sediments and waiting half an hour, waiting for this detector to detect the signals. Or we'll grab a representative sample, we'll submit it, we'll bring it back to the lab, at which point we can analyze it a whole slew of different ways. We can use ICP, we can use a high-resolution gamma spectrometer in the lab, we can look at neutron activation. There's a number of ways that you can get your content, either directly by the radiation emitted or indirectly looking at these actual radioisotopes. And then the big equation to calculate the age for OSL ages. And so I have, after all this work, in the end, and you spend all this time, you've done all the processing, but the actual age equation is so easy. It almost makes it seem like, my 8-year-old son can do this. You go through all that work, but each step really takes a lot more than is actually. I don't have any fancy equations to really show, but you just determine how much dose you need to give the sample to have produced the luminescence it released when it was brought into the lab the first time, and what is the dose rate environment. I'll go into those a little bit more, but anyway, that's in some ways it's a simple technique. But you got to start in the field. You got to collect a sample. You got to know what you're collecting. Collect something that was exposed to sunlight if you're looking at optically reset samples. So there's kind of method to get your sample back to the lab. You can't just put it in a clear Ziploc bag. So typically I'll show you my toolkit. Typically we're walking around with things that if you go through airports, that the airport TSA security guys do not like. We take pipes and we pound pipes into the outcrop, and then extract that to collect our sediment in the dark. On occasion, we do what we call kind of nighttime rogue ninja sampling, where you go out at night with red headlamps. I usually make all my students wear black too, just to add to the kind of the fun of sneaking around into the field and digging into the exposure and collecting in dark containers. But it's once you've seen how to do it, it's not so hard, right? You just it's actually kind of fun to be like pounding pipes into sediment. So typically you're going to use some kind of metal tube or an opaque tube. I do not recommend PVC, even the black PVC. Light can get through. So if you do that, you need to seal your sample. We need to collect another sample surrounding that sediment tube for the dose rate environment. Water content is important, and water will attenuate radiation. So we need to know the time average water content And then for the Cosmo folks, which we sorely need your help because our equations were developed in the 70s or something. We use our sample depth lat long to calculate what, in theory, our cosmic contribution to our dose rate is. Here's a picture of my toolkit, just kind of spread out in a gravel pit somewhere. So you have that big old, you're going to have your metal pipe and sledgehammer, duct tape. All of this stuff, yeah, maybe not the field book. All this stuff you can get at the local hardware store. And so that also, when you're in a pinch, you could just go into town and get most of the supplies you need. I use a 1.5-inch stainless steel electrical conduit that I get from either Home Depot or Lowe's. I make those guys cut it for me. This is a plug. It goes on a galvanized steel pipe. I don't know what you would use it for normally, but you screw it. So it has the threads on the outside, which is very important so that you don't seize your pounding cap onto your tube. Just typical stuff. They have a picture in Salt Lake City International Airport. I think they have a flight to Canada, but they have a picture of my sledgehammer as one of the things that you cannot bring on the plane. I've had a hand trowel taken from me in Corsica. Like all these things, they're really not weapons, but some people think they are. So so the point is your little pipe bomb that you're collecting in the field, you need to ship it home. Do not put it in definitely not in your carry-on. We duct tape the ends of these things. They look really suspicious. And then when they ask you what's inside, you tell them, they ask if they can open and look inside. You say, no, you can't. You can't expose it to light. And so then they take you aside. And so you always have to ship these things home. You put them in your check bags. I've had students who have come to my lab with TSA tape over their OSL tubes, where in the check bag, they opened it up to see what was in it. I don't know if they dumped it out and then put it all back in. It's ruined. So it really, I didn't say this yet, but seconds of sunlight exposure for quartz, and you're down to a 0 age. Doesn't take long. So we're trying to prevent things to get exposed to light. Here's just a picture of people sampling for OSL. So here's that metal pipe and that pounding cap, sledgehammer. I'm going to pound it into the sediment, and then you need to collect that dose rate sample. If you don't have a field gamma spectrometer, you bring back a sample from the field, and so you need to get a representative sample in what's kind of like a little beach ball, 3-dimensional, surrounding your sample tube. Problem is that you'll never get this sediment that's in the free face of the outcrop because it's already been removed by the time you got there. So you need to make sure you do a very good job going into the outcrop face and into the sediment to get that representative sample. Measuring the depth of the sample below the land surface. You can also use other methods like coring, but you'll need to make sure that you can do it in such a way that you don't expose your sample to light. So if you're interested in coring, talk to me first. And then you bring your sample back to the lab. And we're dating the last time sand was exposed to light, so it's a dark lab. And it's not that, I don't know if anyone here has been in my lab. I don't think so. But it's not super dark. We're not feeling around in the dark, working with mixing HF and doing stuff like that. But it is, it's darker than this room. And it's like a photo lab. So if you've we use red or amber light. And that's because quartz and feldspars are most sensitive to the short wavelength, high energy light wavelengths. So blues and greens are higher energy and will zero your sample pretty darn fast. Under orange and red light, we still keep everything tucked away in a cabinet. If you're not touching it, it's stashed away. But you can work and you can see. You learn quickly kind of how to maneuver around without making a mess of things. This is what the instrument looks like. So it is a pretty small desktop instrument. It's actually a black box, which is kind of fitting for a luminescence dating It has a couple of things. Actually, physicists love these things because they build them in their garage, because it's so fun to look at the properties of minerals and how they respond to different things. So, and you can buy, if you're a physics geek, I guess you can buy all this stuff, except for the radioactive source online somewhere. So you have a photomultiplier tube, which just helps detect that weak luminescence given off. Associated with it are a number of light sources of different wavelengths, depending on which minerals you're dating. Heating source for heating steps during the dating process. There is a radiation source. It's a strontium-90, and it's enclosed. It's about the size of a little dime, little coating of strontium-90 that we use to try to replicate the burial dose of radiation. Some computers, computer screen, and then a sample holder, which I have in the next slide, that can hold 48 aliquots. So we call them aliquots. They're subsamples of the original larger sample. This is the old days. This is probably year 2000 when I was just starting my PhD. We used to load these things up and put tons of sand on, but everything's getting smaller and smaller and smaller. So now if we're going to do aliquot dating, we do something called small aliquot. So this is a centimeter, this is also a centimeter across. So there's 25 sand grains on there. And then, a lot of times we're moving to single grain dating. This is, you can put 100 sand grains on this aliquot, and then you usually don't put 48 of those on because the run will crash, and but you'll maybe put 800 sand grains on a run and analyze that. The reason why, so a lot of you guys are hearing about single crystal, single grain, going smaller and smaller, the reason why we sometimes still don't do single grain for everything is that problem I told you about in the very beginning, that you have 100 sand grains, there may be only one that actually luminesces. And so that's a lot of time you're spent analyzing 100 sand grains. You get one result back. So in those cases, we put 25 sand grains on, and every fifth aliquot luminesces. So it allows us to do pseudo single grain dating just because of the response. Okay, so the preparation, like every technique that you've heard about, you need to isolate down to a certain mineral. And we're either going to look for potassium feldspar or quartz. And these are, I put this up, you don't need to know this exactly, but, so we're going to sieve the sample, and we'll remove everything except for the quartz. If you come to my lab, you'll do up to this point. And then when we go and we're mixing and doing things with HF in the dark, I do that step. And I don't have any of my students or anyone do that step. But these are pretty easily done. If you show up for 3 days, 4 days, maybe 5 if you have a lot of samples, you can get through all these steps of sieving and getting down to pure quartz. And we'll check on the instrument if it is pure quartz, if we're looking for quartz, because different minerals have different luminescence properties. And then on the actual, those aliquots I showed you, or the single grain, we just want to make sure that we don't overload our sample. So these are bad examples. We're going to just use a monolayer, 1 sand grain, probably only 25, maybe 50 if it's an aliquot, or make sure there's only 1 grain in each hole if it's single grain. And then here's where the time comes in. So processing, you can process in 4 days. Got pure quartz. Maybe a little bit longer because I've got to show up and do the HF. But within a week, you can have pure quartz. The time is not spent in processing. The time is also not spent in sampling in the field because you pound that pipe, take your notes, and you're done. The time is spent analyzing the samples because we have to go through several cycles of preheating, irradiation, and OSL measurement for each aliquot. There's 27 steps that we do for each aliquot or for each sand grain. And to get an age, we need to analyze, if we're doing small aliquot, 50 to 100 measurements. If we're doing single grain, because most of them don't luminesce, we're going to be analyzing thousands of single grains, doing those 38 steps each time. And So the measurement doesn't take that long. We need to replicate the burial dose of radiation. So we have to dose that sample. If your sample is 10,000 years old, we need to give it 10,000 years of radiation. Luckily, we don't have to wait 10,000 years, but we still have to wait on the order of hours to days to replicate that dose. So a typical sample will take 1 week of dedicated instrument time. I have 2 machines, so I can get about 110 samples done a year. So that's where our time comes in. This is what the luminescence signal looks like from a sample of quartz. So we have turned on the stimulating light source right at this exact instant, and the sample luminesces and decays to a background. And there's actually, I think, 14 different measurements here to go through that measurement cycle. To measure different steps, we need to determine the characteristics of the luminescence. And then so the signal is generated as the first 4 data points on the signal decay curve minus the background. So every sample will have a certain thermal background. The instrument has a background. We subtract that out. This is what the single aliquot regenerative cycle, measurement cycle looks like, what we do. First step is to measure the natural luminescence signal, which is only in luminescence. And then to calculate the dose the sample received during burial, we give it known doses of radiation and determine the luminescence. And from that, we calculate this dose response curve. And then we interpolate, based on that original signal, what the equivalent dose was. So in this case, the sample received about 65 grays of radiation. Based on that, I'm going to guess it's at least 20 to 30,000 years old. So it takes, that's a pretty hot natural signal.
Can I interrupt just to dwell on that for a second?
Oh, yeah.
So I'm sure this is super naive, but so you do the natural signal first.
Yes, and then it's gone.
And then
you will never have it back.
And then in the same sequence, when it's on the machine, then you do this cycling of the...
Yeah, so this is all done on one aliquot. So in the old days, we did something called multiple aliquot technique, where we would grab 5 aliquots and we'd measure this step, and another 5 we'd measure this and this. This is single aliquot dating or single grain dating. So the signal and all these measurement points are made on the exact same population of grains, which is that was that year 2000 mark I put on the. That was a huge step forward. And then in between, what I'm not showing is in between each of these steps, we have to do a test dose where we give it a known dose repeatedly to monitor for sensitivity change. Because the luminescence signal, actually as we're playing with it and we're heating it and we're dosing it, will change over time. So we need to correct for all that. But I don't go into all that here. But we can discuss it. These are some results from a student of mine. It's a really bad example because her uncertainties on her equivalent doses are huge, but it was what I had at the hotel last night when I was putting this together. So what we do is we go through and this is from small aliquot measurements. These are the equivalent doses and the uncertainty on those measurements. And 3 different ways that we display this data. We typically do not use histograms. They're shown here. Histograms, as the luminescence folks, you can mask all this uncertainty. You'll never know it based on a histogram because you're only plotting the midpoint. There's no data or information about the uncertainty on the distribution. So typically we'll present a probability density function with the actual measurement points and their uncertainties. The other thing in luminescence that you'll see if you start to read and look at these papers is a lot of people report their data as radial plots, which take a little bit getting used to read. But basically you have 2 y-axes and 1 x-axis. The x-axis has to do with the relative error. So as you're further out towards the radial plot, these are lower error data points. And then this is 1 to 2 sigma. And how you read any particular data point is you go from the 0 point out to the radial plot. So for example, this data point is probably right around, 3 grays. And this is to help to try to I'd like to present both because it's kind of hard to read. So radio plots, you're looking, if they're all together, it's a nice distribution. If they're within 2 sigma of each other, they're going to be plotted in that gray zone. Also, I could have put up a 2 sigma up here on my PDF also. The next is an example of another small aliquot result. The first one, they were pretty consistent. They were mostly grouped together. This, here's the histogram, here's the PDF. There's a population of small aliquots that are producing younger and consistent equivalent doses and ages, and then you have a bunch that are producing much older results. These are cases, this is from a river environment, a very fast, muddy Holocene river, that these aliquots represent sand grains that were not exposed to light or sufficient light prior to deposition. So this would be what we call partial bleaching if you're reading the literature and someone's talking about partial bleaching. And you can see it here in the radial plot, these guys here, and there's probably another population going way up to much higher equivalent doses, older ages. In this case, we do something called a minimum age model. If we took the average of all this data, we'd get something that was too old. It'd actually probably fall right here when we have no data, right around 10 grays if you took the mean. But instead we go in and we look at and use a statistical model to say what is the youngest population that's statistically consistent to get an age. Usually if I see something like this, I say, ooh, we have partial bleaching. I might want to go the next step and look at single grain results. Single grain results, it's kind of like going with resolution versus precision. So now I've gone down to the age of each individual sand grain. I don't know how many, do I say on here? Oh gosh, I don't know. This is probably close to 100 sand grains. The previous ones were probably 20-some aliquots. So now I've increased my resolution, going down to single grain, but my, I guess the uncertainty on each measurement is much greater. And my scatter has increased too, because now not only am I looking at the light history of each sand grain, now the dose rate environment is different for each sand grain. And I'll never be able to reproduce that. One sand grain might be sitting next to a potassium feldspar or a zircon, have a much hotter radioactive microdosimetry. The next one's sitting in a cold spot. And so we don't see nicer data with single grain data, actually gets messier, but we are able to, if we use one of those minimum age models and known uncertainty that comes with single grain dating, we can pick out that minimum age. So I think, so now I think the previous one had 2.1 grays for the dose, and now we're down to 1.9. So we're probably more accurately looking at the age, but our relative error on our measurements have gone up. Okay, where can you, 1 minute. Okay, where can you date? Okay, you could date a lot of different things. And I'm just going to quick move on. You can see that here's dating range. We can go out to 300,000, maybe 500,000 with quartz, but the big push right now is to go to 2 million. And we can move to feldspars if we want to go older. And I think Greg had said, I'll use Luminescence. Folk have all these crazy papers, and each one, a new one each week in these journals. It's because we're working on methodology right now to try to extend our dating range. We want to go back to 2 million years. So we're looking at different components of the luminescence signal. And here's just an example. Location, radiocarbon, OSL, and cosmogenic, and U-series for carbonates, like surface carbonate soils, all go hand in hand really nicely. So a lot of projects try to link these together because they're looking at different things. The radiocarbon is telling us the age of the organic material, which, a lot of places where I work is older than the sediments themselves. It has to be if you're looking at trees that were burned. The OSL is telling us when it was deposited. So linking that, and I don't have an example where I've thrown in cosmogenic and U-series. Archaeology, really big push right now is to apply OSL dating to archaeological applications. Here's a slab-lined hearth in the Grand Canyon where we had radiocarbon and then the OSL. And you'll notice that the OSL is slightly on the younger side because this is coming from wood from trees that are hundreds of years old when they were burned. So we can fingerprint this a little bit better. There's a new paper out by my colleague looking at dating rock surfaces. So actually kind of doing surface dating with OSL, looking at rock art. This is the great gallery in Canyonlands, the horseshoe member of Canyonlands. This guy, flake of his rock fell off. We were able to find that rock, go in, ninja nighttime sampling with headlamps, hiking several miles in, and then use a pulley system to lift up that clast and go in and sample the rock. And so we chipped off pieces of the surface. Here's a little bit of that figure that fell off. So the actual surface sediments from the surface of the rock, 890 years old. Sediment, when we lifted up the rock, the first sediment we found underneath the rock came back 820 years old, cottonwood leaves. So when we lifted up the rock, there's all these cottonwood leaves that had been flattened perfectly. So we dated those with radiocarbon. And then the latest thing is the surface technique. So where you go in and you date the age as you go deeper into the rock. And you can look at how light's penetrating. And from this, we're able to determine that after the surface was exposed, painted on, and then 700 years later was buried. And so we can bracket the age of this rock art. And then the latest thing that I'm not going to talk about is OSL thermochronology. We're working on it. It's not quite for prime time yet. Anyway, any questions?